So this is the first complex with the coordination number 4, NiCN4 2 negative. First of all, again we are going to find the coordination number or the oxidation number of nickel. In this case, that's going to be X plus 4 into Cn is equal to minus 2. So X minus 4 is equal to minus 2. So X is equal to plus 2. So the oxidation number of nickel is plus 2. That means nickel is existing as a plus 2 ion in this case. Next we go to the electronic configuration of Ni2 positive. The electronic configuration of nickel is 3d8 4s2. So Ni2 positive means 2 electrons are going to be lost from S. So that's going to give you Ar 3d8 4s0. So again, now let's make the d orbitals. That's 3d 4s 4p 4d. Now let us put our electrons of nickel in this. So there are 8 electrons, 1 2 3 4 5 6 7 and 8. Now in the environment of the cyanide, that is the Cn negative ligand, what happens is these two last electrons, they pair up. So when they pair up, this is going to happen. So 1d orbital is now empty on the 3d. So that can be used for bonding. And there are 4 Cn negative ligands. So 4 orbitals which contain the lone pair are going to overlap with 4 empty orbitals present on the metal. So 1 with this, 1 here and 2 here. So that's 1 Cn negative, another Cn negative, another Cn negative and another Cn negative. So the hybridization that we got is DsP2. So that's square planar. This is a square planar complex because the hybridization is DsP2. Now let's go on to the next complex. The next complex in this, what I have changed is the ligand. Nickel is same. You will see that the oxidation number will also come out to be the same. So that's X plus 4 into Cl is equal to minus 2. So X minus 4 is equal to minus 2. So X is equal to plus 2. So nickel has an oxidation state of plus 2. That means it exists as Ni2 positive. So if nickel exists as Ni2 positive, then its electronic configuration is going to be Ar 3d8 4s0. So again, let's make that orbitals of ours. So this is the 3d 4s 4p 4d. Now fill in the electrons of nickel. So that's 8, 1, 2, 3, 4, 5, 6, 7, 8. Now what happened was in the previous ligand, that is Cn negative, the electrons paired up. But chloride ligand does not provide that kind of environment for the electrons to pair up. So these electrons, they do not pair up. And the Cl has lone pairs, orbitals which have lone pairs. So the orbitals still require empty orbitals on the metal atom. So the orbitals they use are this and this. There are 4 Cl, so 4 orbitals they will use. So that gives you a hybridization of sp3. So that is tetrahedral, means this complex is tetrahedral. octahedron. So this is how you can use your valence bond theory to predict the structure, to predict the geometry, to predict the hybridization, and to predict whether the complex is going to use the inner d orbitals or the outer d orbitals in the formation. Paramagnetic fields, as I said, paramagnetic substances are those which are weakly attracted to an external magnetic field. And those complexes which have unpaired electrons, those complexes are said to be paramagnetic. In contrast to this, diamagnetic substances are those which are repelled by the presence of an external magnetic field. And those complexes which have no unpaired electrons, those are diamagnetic. If we look at our previous complexes that we did, okay, let's take a look at this complex. In this complex, you can see there are two unpaired electrons, and these two unpaired electrons, they lead to the paramagnetic behavior of NiCl4 2 negative. So NiCl4 2 negative is paramagnetic. It will be attracted by an external magnetic field. This complex is going to be attracted by an external magnetic field. This complex, here you can see that there are no unpaired electrons. So if there are no unpaired electrons, this means that this complex is a diamagnetic complex. It is going to be repelled by the presence of an external magnetic field. Similarly, we can do for our octahedral complexes also that we previously did. If it has unpaired electron, it is going to be paramagnetic. If it has paired electrons, it is going to be diamagnetic.